Hello students, welcome to the lecture on linear programming, and after this lecture we will be able to learn the following objectives. Understand assumption of linear programming, explain the process of formulation, understand graphic method, discuss the SIMPLEX method, understand two-phase method of linear programming problems. Let us start with the introduction of linear programming. The immediate and more obvious LP results enable the mill operator to minimize the cost of cotton blends, minimize substandard blends, maintain accurate inventory records, purchase and sell most economically. The basis of the LP technique is the formulation of a mathematical model of the allocation problem. For problems of any practical size, this model is entered into a computer and the computer LP system rapidly calculates the optimal solution. The system may also produce reports which indicate the effect on the optimal solutions of possible changes in the given prices, availabilities, specifications, etc. Little mathematical knowledge or skill is required to formulate an LP model. Nor do the operation of the computer and the analysis of computer results require any advanced technical skill. Now we will discuss assumptions of linear programming. The LP problems embody 7 important assumptions relative to the problem being modeled. The first 3 involve the appropriateness of the formulation, the last 4 the mathematical relationships within the model. Objective function appropriateness. This assumption means that within the formulation, the objective function is the sole criteria for choosing among the feasible values of the decision variables. Satisfaction of this assumption can often be difficult. Decision variable appropriateness. A key assumption is that the specification of the decision variables is appropriate. This assumption requires the decision variables are all fully manipulating within the feasible region and are under the control of the decision maker. All appropriate decision variables have been included in the model. Constraint appropriateness. The third appropriateness assumption involves the constraints. Again, this is best expressed by identifying sub-assumptions. The constraints fully identify the bounds placed on the decision variables by resource availability, technology, the external environment, etc. Thus, any choice of the decision variables which simultaneously satisfies all the constraints is admissible. The resources used and or supplied within any single constraint are homogeneous items that can be used or supplied by any decision variable appearing in that constraint. Constraints have not been imposed which improperly eliminate admissible values of the decision variables. The constraints are involatile. No considerations involving model variables other than those included in the model can lead to the relaxation of the constraints. Proportionality variables in the LP models are assumed to exhibit proportionality. Proportionality deals with the contribution per unit of each decision variable to the objective function. This contribution is assumed constant and independent of the variable level. Similarly, the use of each resource per unit of each decision variable is assumed constant and independent of variable level. There are no economies of scale. Additively deals with the relationships among the decision variables. Simply put, their contributions to an equation must be additive. The total value of the objective function equals the sum of the contributions of each variable to the objective function. Similarly, total resource use is the sum of the resource use of each variable. This requirement rules out the possibility that interaction or multiplicative terms appear in the objective function or the constraints. Divisibility. The problem formulation assumes that all decision variables can take on any non-negative value including fractional ones. Certainty. The certainty assumption requires that the parameters Cj by and Aij be known constants. The optimum solution derived is predicated on perfect knowledge of all the parameter values. Since all exogenous factors are assumed to be known and fixed, LP models are sometimes called non-stochastic as contrasted with models explicitly dealing with stochastic factors. This assumption gives rise to the term deterministic analysis. The exogenous parameters of a LP model are not usually known with certainty. In fact, they are usually estimated by statistical techniques. Thus, after developing LP model, it is often useful to conduct sensitivity analysis by varying one of the exogenous parameters and observing the sensitivity of the optimal solution to that variation. Students, let us now talk about formulation of linear programming problems. Structure of linear programming model. The general structure of the linear programming model essentially consists of three components: the activities, variables, and their relationship, the objective function, and the constraints. The activities are represented by x1, x2, x3, and up to xn. These are known as decision variables. The objective function of an LPP is a mathematical representation of the objective in terms of a measurable quantity such as profit, cost, revenue, etc. The constraints. These are the set of linear inequalities or equalities which impose restriction of the limited resources. General mathematical model of an LPP. Optimize maximum or minimize Z by using the formula which is as shown on screen. Guidelines for formulating linear programming model is: identify and define the decision variable of the problem. Define the objective function. State the constraints to which the objective function should be optimized. Add the non-negative constraints from the consideration that the negative values of the decision variables do not have any valid physical interpretation.
The steps. Set up the objective function. Set up the constraint inequalities. Graph the system of constraint inequalities. Find the vertices of the graph. Evaluate the objective quantity at each vertex. Pick out the least or greatest value depending on what your objective was. First, we have to decide what the objective function is. In other words, we have to decide what we want to optimize, either the maximum or the minimum. Start with the example. Bill works for $10 an hour for selling soda and $8 an hour for tasting candy. Bill only has 20 hours of free time to work. He wants to spend at least 6 hours a week tasting candy, but cannot work for more than 12 hours a week. Find the maximum weekly earnings. We want to find the maximum amount that he can earn every week. Secondly, you have to assign variables to the quantities. So for the number of hours tutoring, we have X, and the number of hours tasting candy, we have Y. So we write let X equals number of hours tutoring, and same goes for Y. So here we have the original question, so you can always refer back to the numbers. So after that, we have to assign the constraints found in the word problem. So in the word problem, X, which is the number of hours that he can work tasting candy, is at least 6 hours, so greater or equal to 6, and no more than 12 hours a week, so less than or equal to 12. The same goes for the other one, which is the combined hours of X and Y cannot be more than 20, so X plus Y is less than or equal to 20 hours per week, which is in the word problem. We also have natural constraints. We have natural constraints because X cannot be less than 0 and Y cannot be less than 0, since it is impossible for him to work negative hours at his job. We graph each of the lines right here. So we have X is less than or equal to 6 going down right here, and we have X is greater than or equal to 12. which is right here. And then we have the other one, which is x plus y is less than or equal to 20, and this is the line right here. And since we have the natural constraints, it has to be in the first quadrant. And now we have the vertices, which are each of the corners of the feasible region. So after finding the vertices, we evaluate them by plugging them into the equation one by one. So we have the vertices right here, and then we put it into a little chart. So vertices, we have 10x plus 8y, which was our original equation, and then we have the money made, so which is the final value. So we put 6 in x and a 0 as y, and then we get 60, and that's the money we can make. So you could do this by yourself. It's just simple mathematics. The list of the values for the corner points, which we need since we know that the maximum value is on a corner point. So finally, you have to pick the point with the highest value, since we are trying to find the most amount of money he.
Let us now discuss the steps of solving an LP problem graphically. Step 1. Formulate the LP problem. Formulation refers to translating the real-world problem into a format of mathematical equations that represent the objective function and the constraint set. Often, data gathering, problem definition, and problem formulation are the most important steps when using any tool. Step 2. Construct a graph and plot the constraint lines. Constraint lines represent the limitations on available resources. Usually, constraint lines are drawn by connecting the horizontal and vertical intercepts found from each constraint equation. Step 3. Determine the valid side of each constraint line. The simplest way to start is to plug in the coordinates of the origin O, O, and see whether this point satisfies the constraint. If it does, then all points on the origin side of the line are feasible and all points on the other side of the line are infeasible. If O, O does not satisfy the constraint, then all points on the other side and away from the origin are feasible, valid, and all points on the origin side of the constraint line are infeasible, invalid. There are two exceptions. Step 4. Identify the feasible solution region. The feasible solution region represents the area on the graph that is valid for all constraints. Choosing any point in this area will result in a valid solution. Step 5. Plot two objective function lines to determine the direction of improvement. Improvement is in the direction of greater value when the objective is to maximize the objective function, and is in the direction of lesser value when the objective is to minimize the objective function. The objective function lines do not have to include any of the feasible regions to determine the desirable direction to move. Step 6. Find the most attractive corner. Optimal solutions always occur at corners. The most attractive corner is the last point in the feasible solution region, touched by a line that is parallel to the two objective function lines drawn in step 5 above. When more than one corner corresponds to an optimal solution, each corner and all points along the line connecting the corners correspond to optimal solutions. Step 7. Determine the value of the objective function for the optimal solution.
Let us understand the term unbounded solution. When an LP solution is permitted to be infinitely large, it is known to be unbounded. Let us consider a simple example to understand this term. Let me draw a graph and then I'll draw some constraints. Let's consider the horizontal axis as the x-axis and the vertical axis as the y-axis. Now I will draw the two constraints. Let's say this is the first constraint and this is the second constraint. The constraints have been given to us with a greater than or equal to sign. So this means that the feasible solution region for both these constraints would be the region on the line and above the line common to both these lines. So this will be the feasible solution region for this LP solution, which is nothing but all the points of x and y above the edges O, A and B. Now suppose the objective function is to maximize the profits. Now for this solution, what we'll do is we'll try to draw a family of objective function lines parallel to each other. So we'll start it from the origin and try to move farther from the origin till a point when one of these lines touches the farthest point of the feasible solution region. So if we try to draw these parallel lines and try to reach to the farthest point, as you know that the feasible solution region has an upper limit which is infinitely large, the solution would be lying at an infinitely large point. So such a solution is known as an unbounded solution.
Here, we begin talk about simplex method, the subject of linear programming, sometimes called linear optimization, concerns itself with the following problem. For n independent variables as x1 to xn, look at your screen. A set of values x1 to xn that satisfies the constraints which are shown at your screen is called a feasible vector. The function that we are trying to maximize is called the objective function. The feasible vector that maximizes the objective function is called the optimal feasible vector. An optimal feasible vector can fail to exist for two distinct reasons. As there are no feasible vectors, that is, the given constraints are incompatible. There is no maximum, that is, there is a direction in n space where one or more of the variables can be taken to infinity while still satisfying the constraints, giving an unbounded value for the objective function. Why is linear programming so important? Because non-negative is the usual constraint on any variable xi that represents the tangible amount of some physical commodity like guns, butter, dollars, units of vitamin E, food calories, kilowatt, hours, mass, etc. Because one is often interested in additive linear limitations or bounds imposed by man or nature. Minimum nutritional requirement, maximum affordable cost, maximum on available labor or capital, minimum tolerable level of voter approval, etc. Because the function that one wants to optimize may be linear or else maybe at least be approximated by a linear function, since that is the problem that linear programming can solve. Let's now talk about two-phase method. Artificial variables and auxiliary problem is as shown at your screen. These slack variables are called artificial variables. This new LP problem is not equivalent to P. But if we can force all artificial variables to be 0, then the resulting solution gives a feasible solution to P. So we change the objective function to as shown on the screen. Elementary ideas about duality, see the general linear program as shown on your screen. The variables in Y are in one-to-one correspondence with the constraints of the primal LP, and the variables in X are in one-to-one correspondence with the constraints of the dual LP. The dual of an LP is again the original LP. Theorem 1. Weak duality theorem: if X and Y are feasible solutions to the primal and dual respectively, then see at your screen. Hence, the proof of the theorem is shown at your screen, where the two inequalities hold by feasibility of X and Y. Theorem 2. Strong durability theorem. The optimal objective value of the primal is finite if and only if the optimal objective value of the dual is finite, and in this case the optimal objective values are equal. The basis of the LP technique is the formulation of a mathematical model of the allocation problem. The LP problems embody 7 important assumptions relative to the problem being modeled. The first 3 involve the appropriateness of the formulation. The last 4, the mathematical relationships within the model. This assumption means that within the formulation, the objective function is the sole criteria for choosing among the feasible values of the decision variables. A key assumption is that the specification of the decision variables is appropriate. The third appropriateness assumption involves the constraints. Additively deals with the relationships among the decision variables. The general structure or the linear programming model essentially consists of 3 components. The feasible solution region represents the area on the graph that is valid for all constraints. The subject of linear programming, sometimes called linear optimization,